Well, hello, everybody. My name is Atomic Rob. I want to welcome everybody here to the Center for Creativity at the Tulsa Community College. And I want to thank everybody for bringing good old Atomic Rob out of the lab. I've got some stuff here to show you. Just a few things. Going to bring out of my bag of tricks here. I might need a little help, though. Anybody here? Anybody free to help me out? Yeah, you. Come here. Come here. Come here. Come here. Come here. The name is?
Garrison.
Garrison. Atomic Rob.
Very nice to meet you, Atomic Rob.
Well, I hope so. We'll see. Tell you what, before we do anything, you better put these on.
Will do.
You never know what's going to happen. First off, do you know why your bicycle stands up when you're riding it? Well, hopefully when you're riding it around, it's standing up. Mm-hmm. Yeah, got your helmet on. Why does your bicycle stand up instead of just falling down? Why is it? Do you know why?
Inform me, Atomic Rob.
You probably know this. Garrison, right?
Correct.
Garrison, all right. All right. The thing stands up because of centrifugal forces keeping the thing up. That's what's going on. One finger, I can keep that thing. Oh, my goodness. That is centrifugal force. It's throwing forces out in all directions, and good old Newton was good at the kind of observing that. He didn't invent the forces of motion and all these things. Here, grab a hold of that. Keep your thumbs in. Try to turn it. You feel the forces working against you? Mm-hmm. Isn't that cool? Now I'm going to spin it up even further. I know it's going to be hard, but I want you to force that thing up onto its edge. Put it onto your flat palm, right on the bottom of that. All right, you ready? You trust me?
Uh-huh.
All right. Thank you, ladies and gentlemen. And Garrison, awesome. Man, you almost killed me with that thing. Be careful with these things. You know they put these in missiles. They put these in guidance systems. Yeah, helicopters use gyroscopes and stuff like that. So yeah, Newton, he was into this stuff. Another guy, way back, a guy named Galileo. Let me show you this. He used to sit around in church, big church, cathedrals, right? Curtains, huge curtains and ropes hanging way down, and he would watch them. He'd watch them swaying, right? You couldn't figure out why this one was swaying at that speed and that one over there was swaying at that speed, a little bit faster. This is what kind of it all led to. This is a wave pendulum machine. This is a machine that's set up with 16 different pendulums. That, my friend Garrison, is a pendulum. Just like that stick is a pendulum. How long it takes for this pendulum to go one cycle. Let me show you what one cycle is. When I let go, and it comes back as one cycle. Each one of these has a different cycle, but there's a relativity between the cycles. The deal is with the pendulum, the length and the speed is all, we can predetermine this with math. There's a formula for that. To determine how fast a pendulum swings, it's a simple formula. It would be T equals 2 pi L divided by G. You got that?
That's simple, huh?
Good. That simple. T is time, L is length, G is the mass, in this particular case, golf balls. Now, I've got this set up, hopefully, each one of these, 60 times a minute, 59 times a minute, 58 times a minute. That's how often that golf ball will swing back and forth. Now, if everything goes right, I'm going to use the pendulum of doom. I did tell you this was the pendulum of doom. I didn't tell you. Sorry. All right, here we go. I'm going to initiate this here machine with a bit of a push there. And immediately, the different time zones of each pendulum sets up what we call a sinusoidal waveform. It takes a full minute for this machine to recycle and all of them to come back together. They're going to cycle, though, into groups of 3. Eventually, it will become what looks like a double helix, and there'll be 2 groups that'll split apart. There we go, 2 groups. And it's going to go back through the phases, back from the 3 to, again, we should end up with a sinusoidal waveform, which just about any second now we should start seeing a sinusoidal waveform. There it is. takes a minute for that to go around. Is that nuts or what?
Super
Pretty cool. Thank you, Mr. Galileo. You know he's into space and telescopes too. You going anywhere?
Not now.
Good. Speaking of cool stuff, hold that. That, my friend, is a set of magnets. I have right here what we call a steely in the old days. If you drop that steely, what we call a ball bearing or a steel ball, it should fit right down that tube. Let me put my hand down here to catch it. That was free fall. Did you see how quickly that went?
Yep, just in and out.
See if you can count how many seconds it takes to go from there to there. Are you ready? And go. 1001.
So a fraction
Not
of a
quite
second.
of a second. Right. Good. Now, we've got this bit of metal. These are what we call rare earth magnets, neodymium magnets. They don't stick to copper because copper is not what?
Magnetic.
Ferric would be the actual term. This is the magnet. It's always magnetic. Whoa. This is never, unless we make it so. And there's your clue. Take that, drop it down the middle of this, and as soon as you let go, let's start counting. Ready? Go. 1001, 1002, 1003. Clearly it took longer. 3 seconds, almost one more time. And go. 1001, 1002, 1003. Why is it taking so long to get through that tube? Let me show you. You know what that is?
I do not.
Chunk of aluminum. Pretty cool, huh? Worth
Yeah.
a couple of bucks, maybe. I don't know. You'd probably defend yourself with it if you had to, but I
It
wouldn't.
serves multiple purposes.
It's better for science. Now, what I'm going to do is I'm going to set this right here, and we're going to see something kind of interesting. Aluminum is the same thing as copper as far as magnets are concerned, right? They don't care. But if I drop this, I'm going to rake this. Now, if I put it straight down, it's just going to fall out because we don't have a tube. But we want to look inside to see what was going on there. Here we go. I'm going to drop this right here. Hopefully they can see this. Put your hand down there to catch it. And you see that? It's the same thing. Oh, that was gravity. Thank you, Newton. Now this is virtually the same thing, only we can't see what's going on in there. But with the aluminum bar, we can definitely see what's going on here. What's going on? This is called Lenz's law. L-E-N-Z. Mr. Lenz figured out that if you took a magnet and you dropped it down something that wasn't necessarily ferric, but was conductive. Copper and aluminum are great conductors. We use them in wiring in your house, in buildings, and all kinds of stuff. The fact that they're conductive and the fact that this is magnetic, people like Maxwell and Faraday, they all told us that when we move them next to each other, we create electricity. When we create electricity, we also create magnetism. So what's happening is there's a wee bit of magnetism, just enough to hold that magnet in place. Pretty cool, huh? Now, the last one. Atomic Rob needs to put on his glasses because we're going to make a mess now. Are you ready?
Absolutely.
All right. Now, we've got a couple of things going on in here. We've got the hydrogen peroxide. Now, this is not your run-of-the-mill grocery store hydrogen peroxide. This is the stuff you get at the beautician. The peroxide that you find at the grocery store is about 3%. This is more like 30 to 40%. I've also got some detergent in there. That's what's making it blue. And we can just see that. You just have to trust me. Otherwise, there's otherwise you'll have to smell it and stuff, and you never ever smell.
Nope.
Ever smell anything in chemistry. Also, always wear your goggles. So, shall we? All right, here we go. This is what we call elephant toothpaste. I've got a little bit of yeast in here that's all wanting to be bubbly and release oxygen. This has lots of oxygen in it. The hydrogen peroxide has a lot of oxygen. We're going to release it all at once, but we want to make it cool. So let's do this. Grab a bottle. We're going to make a little bit of color going down the inside of that bottle. This flask. This graduated cylinder. Let's do one more. All right. This is why it's called elephant toothpaste. It's going to make a mess, so I'm going to put this underneath it. I want you to pour that yeast water into this mixture, and we're going to see something happen very quickly, I hope. Oh, it's happening. Oh my goodness, that is what we call elephant toothpaste. See how the oxygen is being really quickly released from the hydrogen peroxide. It's actually making this a little bit warm. You want to feel that? It'll turn you a little bit blue, but it is a little bit warm. Isn't that weird? Mm-hmm. And that is from the immediate release of oxygen from the hydrogen peroxide. And sometimes we get nice little stripes of colors. We got a little bit overboard with it, but hey, what can you say? That's pretty atomic if you ask me. Hey, thanks for helping out today. I really appreciate it.
Very welcome.
Got all your fingers, 1, 2, 3, 4, 5. Good. We got all of our fingers. Everything is still intact. Hey, everybody, thanks for coming out here. It's been awesome. Tulsa, it's like a center for, this place is just crazy. The creative, what is this place? The Center for Creativity or something like that? Is that what you said that? I love it. I want to come back. I want to come back.
You're welcome.
Thanks,
back.
man. Good night. Somebody else clean that up, please.